video about periodic table trends. The periodic table has many patterns, or another way of saying it is many trends that occur going across a period, which is going this way, also called a row, and going down a group. There's also many other trends we've studied before, such as sides of the periodic table, for example, metals, nonmetals. But we're going to talk about two specific trends today, atomic radius and ionization energy. So let's start with atomic radius. Atomic radius, like you've heard before in math class, radius measures the size of an atom. So if you notice here, I've got some board drawings of different atoms. And this atom is medium size, this one's much bigger and a lot smaller. So if we were to take the size, right, a radius is from the center of the nucleus to the outer edge. For now, we'll say that that's a good measure of the radius, except we're not going to be measuring exact numbers of the radius, rather we're going to compare them and talk about a trend that we see. Are things getting bigger or smaller down a group across a period is how we're going to be talking. So let's actually take a look then and see what is occurring. So if you notice here, I've sketched the periodic table, and as you go down a group, the size of the atom increases. And I think this is kind of obvious to see why. Well, every time I go down, I have another energy level. Remember, these numbers on the side are energy levels. N equals 1, so there's one energy level. N equals 2, two energy levels. N equals 3, and we keep adding and building. So our Bohr model that we see here with the rings is kind of a nice way for us to represent this, though we know it's not perfect concentric rings, but it works for this. So, and on the 5th energy level, 5 energy levels. The 6th, there's 6, and look how huge a 7th energy level atom is. So that's easy. It's important to write that down. So let's stop for a second and write that down, that as you go down a group, the size of the atom, also known as the atomic radius, right, increases because you're adding more energy levels, thus making the atom larger. Okay? All right, well, how about going across? Let's bring back our picture again. As I go across, you clearly see that the size starts to decrease. Well, what's the reasoning for that? When you think about it, what's happening as I go across a period? So let's take a look at across a period. Okay? As I go across a period, if you notice, I picked the 2nd energy level. How do I know that? Because I've got 1 ring, 2 ring, 1 ring, 2 ring, 1 ring, 2 ring, 1 energy level, 2 energy levels. So I picked going across the 2nd energy level as an example here. And if we look at that, we've got lithium, and there are 3 protons in the nucleus. Then next to it, we've got 4 protons in the nucleus. Remember, the atomic number goes 3, then 4, then 5, then 6, then 7. And it's equal to the number of protons I have in the nucleus. So as I go from left to right, I notice that my protons are increasing. Well, look how many more protons I have over here. Well, what do positive protons and negative electrons do? They attract. So maybe we can remind ourselves that the positive protons are attracted to the negative electrons, right? And the electrons are out here in these energy levels, okay? So as you go across, what starts to happen is there's an attraction between the nucleus and this electron, attraction, right? How do you increase that attraction? Well, add more positive charge. So over here, the charge in the nucleus is really big, so it can actually pull this one electron in much closer to it. And that's what happens, is that this positive nucleus starts to pull, to tug on the rings, right, where the electrons are, and bring them in closer, more powerful nucleus. So as you go across a period, the atomic radius decreases because the protons in the nucleus can attract those outer electrons in, right, can pull them in closer, more protons, right? And when you pull the electrons in closer, think about it, the energy levels are moving in closer then. That's where the electrons are, making the atom smaller. Okay, that's atomic radius. Next, we're going to talk about ionization energy, which is a new term for us. And again, we're going to talk about how the pattern is seen down a group and across a row. That's our two things, down a group, across a row, or a period it's also called. So keep that in mind, okay? So let's take a look at what ionization energy means before we discuss its pattern, its trend. So if you hear in the word ionization is the word ion. And so that kind of gives away the definition. Ionization energy is the energy needed to become an ion, right? So that might be helpful if you circle ion because it helps you with the definition. Now, which ion are we talking about? Well, a cation, because it's the energy needed to remove an electron. So if we have sodium here, some sort of ionization energy is needed to remove that one electron for it to become into an ion. See, here's the electron removed. There needs to be some energy for that to happen. This energy has a name. It's called ionization energy. Ionization energy. I like to abbreviate ionization energy as IE. So you'll see that later on in the video. Okay, so before we talk about the patterns of ionization energy down a group and across a row, I'd like to introduce this topic that is going to be used for ionization energy, and that's called the shielding effect, okay? So let's think about what the word shield means, right? It means it's like this barricade that protects you, right? If you hold a shield in front of your face, then it's protecting your face from the outside, right? That's what shielding effect is in our atom. So if you notice here, I have my atom, just kind of drew part of it, cut it in half. And I have my nucleus, and here are my energy levels. And if you notice here, these inner, we call these the inner electrons. These inner electrons on these inner energy levels are shielding, are blocking the positive nucleus charge from the outside valence electrons, okay? So they're kind of blocking it. Well, what happens when the positive charge is blocked? This electron doesn't feel as much of an attraction. The more shields you have, right, the more energy levels, the more blocking. So this electron, again, doesn't feel as much of that positive charge. Remember, there's an attraction here. But if you put things that interfere in the middle, then they're blocking and there's not as big of an attraction. Okay, there's still some attraction, but not big. That's called the shielding effect. Okay, so now let's actually go back to ionization energy. Remember, we said down a group and across a period. So, down a group, the energy needed to remove an electron decreases. I don't need as much energy is another good way of saying it. I don't need as much energy. And you can write that. Don't need as much energy. And as I go across a period, ionization increases. I need more energy to remove an electron. Well, why? Well, if you remember about the other trend about size, it has to do with a similar explanation. So let's take a look at down a group. Okay? So here is down a group. Well, look, once again, it has something to do with energy levels. More energy levels. Well, what does that do? Well, think about it. That's more shielding, right? Over here, one energy level, no shielding. Here, one layer of shielding. Here, 2 layers of shielding. Here, 3 layers of shielding. More and more shielding. So as I shield, right, let's take a look at shielding a little closer. If you notice here, here's my nucleus. I have 1 energy level. There's basically no shielding. This positive and negative are so close, they're so attracted. So how am I going to get this electron to pop off? Well, I'm going to need a lot of energy. As you go down a group, more and more shielding, I don't need as much energy. Why? Look down here. I've got so much blocking happening here, so much shielding, that this electron doesn't really feel that positive. So it kind of is easy to pluck off. Remember, ionization energy is the energy needed to remove an electron. So as we go down a group, we add more energy levels, which increases the shielding. And you should explain what shielding is. it blocks the charge of the nucleus from the outer valence electrons. So those electrons don't feel as much of an attraction to the nucleus, and they're easy to remove. So I don't need as much energy. Energy decreases, ionization energy. Okay, and the last part, going across a period. Well, it's a similar reason to atomic radius, okay? Though the trend is different. I need more energy to remove an electron as I go across. I'm going to need more energy to remove this than to remove this. Well, if you notice, 2 energy levels, 2 energy levels, 2 energy levels, 2 energy levels, right? This is a picture of the atom. So it's not because I have more energy levels as I go across a period. But what's the reason? Well, 1 proton, 2 protons, 3 protons, 4 protons. Remember, as you go across the period, your number of protons increases, right? Because your atomic number increases. So 1 proton attracting an electron, don't really need that much energy. 2 protons attracting an electron, a little bit more energy. Ooh, 3 protons attracting an electron, I need a little bit more energy. And wow, 4 protons are going to be very attracted to that electron. I'm going to need a lot more energy to remove this electron. So as you go across, the positive charge, which are the protons, increases, causing greater attraction to the electrons. So more energy is needed to pluck off that electron. And that's the end.